Here we go. Okay, so let me start with quantum dots. So quantum dots have been around for about a long time now. These are colloidal quantum dots, which we make chemically, as opposed to the quantum dots that are made using epitaxial growth that are usually studied by the physicists. So these are made in solution, and they're little boxes of semiconductor that are about 5 to 10 nanometers in size. And the main attribute of that is that if you create an excitation, meaning that you put energy in there, and usually this is the form of light by putting a photon in there, you promote an electron from the valence band, which is filled up, to the conduction band, and you create an electron which is delocalized as a wave function, and it looks like this basically, in the conduction band, and you leave behind a hole, the absence of the electron in the valence band. And as you squeeze, as you go from a large box to a small box and you squeeze it, this wave gets smaller and smaller and its energy gets larger. And so you see this is quantum mechanics in action. You see this in the colors of the light that comes back out when the electron recombines with the hole that comes back down in energy and emits a photon. And you see the light shift from red to blue in this material, which all the same, in this case, cadmium selenide. This material has been around, as I said, for many years, and is now in applications. It's in Samsung TVs as the way to make the green and the red light, the high-end TVs. The prototypical material has cadmium in it. The TVs have indium phosphide in them, as opposed. But this is still the material that we've used and that has been the subject of most of our research up to date. So it's really all about the exciton. So what is an exciton? Exciton is an electron-hole pair. As I mentioned, this electron is delocalized over the whole volume as a wave, a single wave, and for the lowest state, and the hole is also the same thing. And you create the exciton either by shining light. This is the way to put the energy, or you can inject an electron or hole directly into that particle to create your excitation, or your exciton in this case here. When the exciton is done living and it's interacting with the photon field around it, then it emits light, which is redshifted from the light that you're excited with, and that's the basis for the applications that are commercial today. You can also get the electron and hole out from their confined state, and if you have light and then electrons and holes out, that's the basis for making a photodetector or a solar cell. You can have multiple excitons, those are called bi-excitons or multi-excitons. So you can cram in multiple electrons and multiple holes. Each one is a separate wave and they interact with each other. So there's an interaction energy. There's a Coulomb energy between the electron and the hole. There's a Coulomb repulsion between the electrons, and all these come into play, and you can build simple models of just a particle in a sphere with an effective mass in the small sphere with simple Coulomb interactions, and you can mimic the properties of these quantum dots pretty well just with these simple models. Okay, so that was the past. In the last few years, we've been working on a new kind of quantum dot made out of perovskite materials. And these are really interesting materials, as you may know, because they've been especially interesting in the solar cell area. They have better than 25% power conversion efficiency, which is getting close to silicon and all these materials. They're highly defect tolerant, so you can put defects in there, but nevertheless, they still manage to transport electrons and holes quite well. And we make perovskites out of, quantum dots out of these perovskite materials. In particular, we make them out of cesium lead halide. Let me disable high floating. And the interesting thing about these materials is that they behave very differently from the previous quantum dots. You still make excitons in them. The size is now fairly large, compared to about 10 nanometers. which means that this electron that we put in there is not really localized by the size of the box. It rattles around, and by rattling around, it enhances its ability to absorb and to emit light. And the interest we had in there was, can you make these material as a source of indistinguishable single photons, little packets of light? And let me give you a very quick introduction on why this is interesting. So if you have an atom in vacuum, and you create the excitation by taking an electron from the ground state to the excited state, there's a coherence. There's a memory of the phase of the state as the electron goes from the ground state to the excited state. And this memory lasts until the electron goes back to the ground state and emits a photon. So the coherence time, which is called T2, is related to the time it takes for the electron to go back down, which is T1. So in vacuum, you have T2 is equal to 2T1, and that's the best you can do. And when you have such an atom or a collection of atoms, when the photons come out, they come out as wave packets, where the width of the packet is determined by this T2 time, and each packet is indistinguishable from the other packets. And basically underneath the packet, you've got your wave that is sitting, the electrical wave, basically electric field wave that's sitting underneath. Now, people have worked very hard to try to get this kind of system into the solid state, and there's certainly some beautiful systems out there that I won't talk at all about. But in the solid state, what you have sources of noise. You have sources of noise that interfere with the coherence between the ground state and the excited state. And these are called, these time comes in as T2 star. That's an additional pathways for removing the coherence. And this could be if that electron that is sitting in my box, let's say, interacts with vibrations that are inside the box. They scatter off vibrations, or the electron has a spin. And if there's atoms in there that also have spin, is the equivalent of a spin bath, and there could be an interaction between your spin of the electron and the spins that are inside your lattice. And these can happen at very fast timescales. And so when you look at your T2 time, now the T2 time, you have this relationship, 1 over T2 is 1 over 2T1 plus 1 over T2 star, where the T2 star is the timescale of these interactions. That reduces the coherence time and prevents it from being as long as twice the T1 time. As a result, the photons that come out now all have different coherence times, depending on the interactions that happen with the lattice. And you no longer have indistinguishable photons. They all have slightly different T2 times. They're different wave packets, and you can now tell them apart. And that makes a big difference in terms of quantum optics if you want to do experiments with these. Also, there could be reduced single photon purity in these materials. So you can create two excitations, two excitons, let's say, and they interact with each other, and they can both decay to the ground state together, and two photons come out at once instead of one at a time. So that would be reduced single photon purity. Or you could have an absence of a photon where you have a pathway which is non-radiative, and then you have a photon missing. So all these things will hurt you. And so in the case of perovskite materials, what we found was that they were really unique in terms of quantum dots, in the sense that they could begin to fix a number of the issues that are in the solid state. We're still at the beginning, so there's still many issues. But if you look at one photon, that one quantum dot, let's say, and you look at the light coming out, you find that the brightness or the quantum yield is close to 100%, which means we're not missing any photons. That if you do a certain experiment that counts the number of bi-excitons, the number of times you see two photons coming out once, which is called the single photon purity. You look at this 0 here, there's no peak here in this particular experiment, which means that there are no two photons coming out at once. You look at the intensity fluctuations, and that doesn't look so great. That means there's noise in terms of the brightness of that photon that comes in over time. And then this is the energy fluctuation. So this is energy on the y-axis, time on the x-axis. And you see that the energy floats around. That's because your exciton, that wave packet inside the quantum dot of electron, is interacting with the environment, with the electric fields in the environment. And as it interacts with the environment, it changes its energy. So the energy fluctuates. These are all things that eventually we could potentially fix by, for instance, putting electric field and having a feedback circuit to get back to the energy that we wanted. What makes these quantum dots very special is that once you create your excitation, the lifetime of the excitation is very fast. So we've measured it for a number of quantum, this is quantum dot 1, quantum dot 2, quantum 3, etc. We find that it's on the order of a few hundred picoseconds, which is many orders of magnitude faster than the usual quantum dots that we study. And that has to do with the ordering of the states, of the electronic states in the material, where usually the lowest state is a spin forbidden state. Once you create it, it takes a very long time for it to get back to the ground state because of fundamental rules in quantum mechanics. But in this case here, the lowest state is an allowed state, spin allowed, so it just goes right back to the ground state. And that allows this T1 then to be quite fast, fast enough that these other processes, these noise processes, it may end up being on the same order as these noise processes. And in fact, when you measure directly the coherence time, and we do this by sending photons one at a time through an interferometer and letting each photon interfere with itself. So these packets of light, these wave packets, go into this interferometer. And because it's a quantum mechanical process, that wave packet interferes with itself, and you can change the path length of one of the arms of the interferometer. And if that arm is longer than the size of the coherence length of the wave packet, then the wave packet can no longer come back and interfere with itself, because it's like if you have your wave packet and other wave packet here, and they're separated in space, they no longer see each other. If delta is equal to 0, then they exactly are on top of each other, and so you have full interference. So from this kind of experiment, you can measure an interferogram, and then the decay of the interferogram tells you about the coherence length or the coherence time. Length and time are related through the speed of light. And then you measure on this right side here, you measure the decay, and you find that the T2, the coherence time, is on the order of 80 picoseconds. So this is for one dot, and this is for another dot, 55 picoseconds. So we measure a lot of them. They're all on the order of 50 to 80 picoseconds or so, which is not that far away from the 200 picoseconds of T1. And so there are ways to make T1 faster, for instance, by putting the material into a cavity where where we can change the density of states for photons, for light, to make it overlap with the photons that want to come out of the particle. And so putting them in a cavity, that's called the Purcell effect. And then if we can do that and make T1, let's say even just a factor of 10 faster, which would be okay, then we can do an experiment called a Mandel experiment, which we take two wave packets, photon wave packets here, 1 and 2, that are supposedly indistinguishable. And the way that you can tell that is if they overlap spatially in this beam splitter here. So if we change the distance of one of them relative to the other until they overlap spatially, then they become entangled. So if they're identical, then they become a photon pair which is entangled with itself, and they come out together out of this beam splitter. If they're different, if you can distinguish them apart, then the way they come out of the beam splitter is statistical. So one can come on top, one can come on the side, but if they're entangled, they both come out together. So this is an experiment that is a proof that you've created the indistinguishable photons. So this is one area where we're playing with, wave packets inside the dots, wave packets of photons. There's noise coming in from the matrix itself that the dots are staying in, creating disorder. And this is one of the areas that we're interested in. I want to skip and spend another 5 minutes or so in a different material, which also has disorder and exciton properties that are quite interesting to us. So these are J aggregates. So J aggregates are molecular aggregates that are ordered, and they were discovered back in 1936 by a guy named Jelly. And if you, and that's why they call J aggregates. J is from Jelly. If you take a molecule, an organic dye molecule, the arrow here is for the transition dipole moment from going to the ground state to the excited state. And it might have an absorption spectrum. This is from his paper in 1936, which is broad. But if you take these organic molecules and they organize head to tail, such as this, then they couple with each other in a way that you get suddenly a delocalization of the excitation, or the exciton in this case, and it now lives over all of these wave packets at the same time, or the excitation gets and then you get this very sharp line that's highly redshifted. You've decreased the energy because of the delocalization, and the delocalization also ends up minimizing interactions with the vibrations, with the atoms that make up the molecule. And now you have this excitation that basically lives and travels over the details, the atomic details, and which is why you end up with this very narrow line that no longer, because the breadth of the line for the monomer is due to the interactions with the vibrations or with the atoms in the molecule. So you've lost many of the interactions here. So this is an interesting system. It's interesting. So the one we study are these tubular G aggregates made of these psi dye molecules. And they're interesting because in some ways, there are natural systems. Chlorosomes that are found in green sulfur bacteria are these antenna systems made out of chromophores like the dye molecules that very efficiently transmit energy. So a photon comes in, creates an excitation, and gets transported. It can be transported over microns to a reaction center to create photosynthesis. So nature has been using these down in the deep sea to efficiently transport energy. And also there are potential device applications in energy harvesting, for instance, from the sun, et cetera. Very much like what the nature has done. So one is interested in understanding how the transport properties of excitations as they travel down these tubes happen, and other photophysics issues. So you can model these things in a very simple way as bricks that form a helix on a tube. And these are the details of the molecules, and they're basically, you can model them as bricks. They're all negative charges out, the hydrophobic on the inside. And this is what they look like. There's these long tubes that are many, many microns long, and they're almost perfect tubes. You can go in there and you really can't see any defects on the microscope, although there must be some defects in there. You can tell the spectrum gets very redshifted, and you see these bright, sharp lines in the absorption that correspond to this J aggregating effect, where the excitations get delocalized over many, many monomers. The outer peak here comes from the outer wall, and this is from the inner wall, because these are double wall tubes of J aggregates. Okay, so now you have these interacting transition dipoles. The lowest one, where they're all aligned, is the one that gives you this very bright state at the very bottom. It's allowed, it can emit very fast, on the order of a few hundred picoseconds also, and it gives you the bright one. And so you basically, you can model this as a simple Hamiltonian, where you have your energy, site energy epsilon for each dye. Then you have coupling between nearest neighbors, J, and then zeros for all the couplings between non-nearest neighbors. And so if you insert a excitation on one dye molecule and you let this Hamiltonian propagate in time, you find that very quickly that excitation then delocalizes over the whole aggregate of molecules. The reality is that the system is not perfect. There is disorder. There's energetic disorder between the sites based on the fact that your G aggregate lives in a solution. There are other things around, there are electric fields. This disorder can be static, or it can also be dynamic. In the case here of a static disorder, you find that if you then have site energies that are somewhat different from each other, this delta E is the distribution of site energies. When you propagate in time, you find that the excitation localizes now. It doesn't delocalize over a whole tube, but it localizes, in our case, on the order of 100 monomers or so, 100 molecules. And then that excitation, if you have thermal energy, that excitation can start to diffuse around. Okay, at low temperature, you're frozen to that amount of delocalization because of the static disorder. But as you thermally put thermal energy, then the static disorder gets overwhelmed by dynamic disorder from the thermal energy, and you can break down these barriers for transport, and you can have hopping transport. So you can, at low temperature, you have coherent transport, which is band-like and limited by the static disorder. And at high temperature, you have the incoherent transport, where you have that exciton now localized because of the static disorder, hopping between sites, mediated by the bath. And there's a belief that there's an optimum temperature where both methods of transport are active, and that this optimum temperature maximizes transport. And that we don't know where that temperature is in our system. It's probably fairly low, and we're looking at actively putting in some static disorder to get that temperature a little higher up. So that's one case where transport disorder comes into play. There's another interesting observation that we've made, which has to do with when you put energy at room temperature in these materials, you find that the ability of that material to emit light increases. It photobrightens, so it gets brighter and brighter as it emits light, as if you've destroyed or you've gotten rid of defects in the material that prevent that sites where the electron and the hole, that exciton, could recombine without emitting a photon. And so when we went to try to understand this photobrightening, we found that it really only happens at room temperature. You have to have enough thermal energy. At low temperature, the photobrightening disappears. So you're basically in a static regime, where your lattice is static. So you need to have a little bit of fluctuation in your lattice in order for this photobrightening to happen. And the model that we have is that so a photon comes in, you create your exciton inside your lattice. So it's localized, but it can move around. And so at the beginning, before photobrightening, it's moving around and it's finding a site, which is a defect site, and then it gets destroyed without emitting a photon. But if you have thermal energy around, what can happen is that you can have an interaction between the excitation and the lattice can sort of collapse around the excitation to lower the energy and localize the excitation a little bit further and prevent it from moving around too much and finding the defect. And that this structural transformation due to the interaction between the exciton and the lattice can stick around longer for quite a long time. In fact, when we turn off the light, it takes a long time, many hours, for the photobrightening to disappear. And so these essentially defects that are part of the lattice now, but allow the exciton to find these spots and stop moving around as much, that allows then the material to be brighter and to prevent the exciton from seeing the defects that would result in non-radiative recombination. And so energetic disorder has a very strong effect on exciton behaviors in these J aggregates. This particular aggregates that we study has very low disorder, very high exciton transport on the order of tens of microns at room temperature, which is really, really long, much longer than any other material that we know. This photobrightening appears to be an interaction between the wave packet of the exciton and the lattice, which then creates disorder in the lattice, but disorder in this case, which is a positive disorder in the sense that it allows that excitation to get trapped, but without causing it to recombine non-radiatively. Okay, so these are the people in my group from a time where we were able to socially not be distant and not wear masks and have fun in the winter, which may or may not happen this January. Okay, I'll stop sharing my screen here and have the discussion.
Thank you so much, Professor Bawendi. So let me open the floor for discussion, question, comments, or anything. A again, as before, just unmute yourself and when you speak, or if there's a discussion already going on, you have something you would like to say that might not be directly related, you can type in the comment, the chat bar. I will look it up, or press the raise hand button on the Zoom app.
Okay, I have a question.
Yes.
Thank you for this very exciting talk. In the last model that you presented, where you have this molecule that align the excitation that go delocalize on coherent lines. The model that you showed for basically the interaction, the Hamiltonian is essentially a Laplacian. It looks very much like a Laplacian, a 1D Laplacian.
Yes.
Which means that you don't account for interaction that might be for neighbors in the in the lateral direction, if you see what I mean.
Yes.
There is no neighbor in this. There are only neighbors in the
in one dimension.
In the line. So,
yes.
Yes.
Yeah. Yes.
So
yeah.
How accurate is it, and how? Because if you assume that you have some kind of disorder in your system, you would assume that okay, you have neighbors in all directions, more or less, or.
Yeah. So that's a very interesting question. It's accurate enough to give us qualitative understanding of what's going on, but it certainly isn't accurate enough to explain exactly everything we see. So our system is a tube. So it's a two-dimensional surface, and the transport actually goes around a helix. So it's not really one-dimensional along the tube, but it's this kind of two-dimensional excitation that sort of wraps itself around the tube.
Okay.
And so we've done some experiments, and I've asked my student Megan Klein to be on the call here in case I spout nonsense, so she can correct me. We've done experiments to look at the dimension of the transport, dimensionality of the transport, and it's in between 1 and 2, the dimensionality.
Okay.
So clearly, the one-dimensional Hamiltonian I presented isn't quite right, just because of that.
Because if you have this static disorder that you presented, like this epsilon 1, 2, 3, but you know that in 1D you're going to have like a strong localization at a very precise localization length. If you have a bit of 2D interactions, then immediately, okay, you might have localization as well, but the localization length has nothing to do with the. So it totally changed the paradigm. It might be that for a real sample, actually you go, but what you say is that it doesn't happen. It's mostly 1D.
It appears.
One and two. I'm sorry, it's the same question. What does it mean, the dimension between 1 and 2? How do you see it at the level of localization lengths, at the level of phenomena? I mean,
so maybe Megan, you can chime in on how do we see what was the experiment that was done?
Yeah, so the question of the dimensionality is actually something that there's sort of a full paper devoted to, and looking at what level of interactions are important in this excitonic behavior. And so you're correct that this simple model is just a one-dimensional Hamiltonian. It's primarily used for linear chains, but we can extend it as a rough model for these tubular aggregates because they're quasi one-dimensional. That being said, though, in order to more fully model it, you can start adding in more neighbor interactions representing higher dimensionality. And that was sort of done through theory to compare to the experimental spectra that we have for this aggregate. And you end up finding that that dimensionality lies between about 1 and 2. And so because it's the short range coupling that has the much greater effect on the aggregate, it doesn't affect the delocalization length as much as you might expect having that higher dimensionality, but it will allow for changes in something like transport. So say that you have this nanotube and you have a trap site along the way and the exciton can't delocalize or can't diffuse past that. Because it's quasi one-dimensional, it can actually go to a separate spot on the tube, go past that, and then keep transporting. So it actually likely lengthens the transport length.
Can I just ask about simple numbers, Megan? Yeah. That is, how many monomers are there, and how to get all the way around one rotation of the helix? How much do you go? So in other words, how big are the tubes and how long in terms of monomers?
The tubes are about 13 nanometers in diameter. With the angle of the monomers, you actually end up going a long ways lengthwise to wrap around. So I want to say to make one rotation of the helix, you end up going a few tens of monomers.
10, it's like 20 monomers or to circle around?
Roughly, I think, yeah. So it's on the order of nanometers to make a full rotation. And then it's maybe on the order of 10 monomers in circumference.
And how about the length that you're talking about relative to the number of monomers, just if they were straight?
The tubules themselves are incredibly long. They're about a micron long, so.
And how long is a monomer?
About 0.2 nanometers, so thousands of
Okay, they're unbelievably long.
Yes.
Okay, all right. Well, so it looks like, feels to me like a 20 by incredibly long strip. More
Yes.
one-dimensional than two-dimensional.
Yeah, and the delocalization of the coherence length is about 100 monomers, right, Megan?
Yes, yep.
So when we create the excitation, it's initially delocalized over 100 monomers. So it's wrapped around the tube multiple times. And then from there, it begins to delocalize further, right? Or transport in these weird ways. And so the transport that we've measured transport at room temperature and found that exciton then can carry energy over microns. We measured 50 microns, but that's probably too long to be quite accurate.
Okay, can I? This is Richard Friend in Cambridge. Hi.
Hi, Richard.
Hi. Good, fascinating, beautiful work. What is the luminescence efficiency for these J aggregates? How there's a number which is not necessarily 100%.
No, J aggregates don't emit very well, but Megan can probably have a number that's better than what I can say. After photobrightening, yeah, go ahead.
Sorry, I believe these before photobrightening are about 18% quantum yield. So.
And do you know what goes wrong?
There's not a clear mechanism for where that loss occurs. One of my colleagues is actually working on trying to rigidify the backbone of the cyanine molecules to remove sort of like a rotational degree of freedom that might be a possibility for where some of that energy is going. Also, some of the work on this photobrightening suggests that trapping the exciton increases the quantum yield, which suggests that there might be sites along the aggregate that are effectively acting as non-radial recombination sites.
Yeah. If you could get the if you could get the yield perfect, then of course these would be fabulously good antennae for all sorts of things like cameras or solar cells.
Yes. So that's part of the push for rigidifying the backbone of the dye molecules, because it's known that the individual monomers in biology, these sort of dyes are used as fluorophores with very high quantum yield, and they take the side dyes and rigidify them.
Yeah.
So that's known at the individual monomer level what goes wrong in a sense.
So can I turn to your foray into the perovskites? I
Sure.
wonder what they're a fairly messy world compared with the relatively well-defined 2-6 systems.
Oh yes, right. But they're very interesting too.
Yes, well, we've all been playing with them, slowly getting lead poisoning. We think they're very soft materials. They're quite strong. We think that for example, the Urbach energy is strongly temperature dependent, which suggests that the dominant disorder at room temperature is due to thermal displacement of atoms or ions in the crystal. I seen you have some quite specific phonon peaks in your luminescence for the dots.
So this is low temperature. These are not, I don't believe these are phonon
Oh,
peaks.
hang on, it's low temperature. You've got some
Low
specific
temperature,
one.
yeah. So
Yes,
these
right.
are fine structure. These are fine structure peaks.
Yes, yeah.
Yeah.
And you're working with relatively large crystals. So there
Yes.
isn't much size confinement, which
That's
probably
correct.
is a help, isn't it? That actually gives you less sensitivity to disorder than you generally are doing with the 2.6s. Yeah.
That's right. So the quantum confinement is minimal in these materials, and you've got your exciton that rattles around. If it were too big, then you'd run into a problem because you probably find more defects and therefore non-radiative. That would break the coherence size of the excitation.
And of course, for the 3D systems, the general description is not very excitonic.
That's right. That's another point, is that if we keep them small enough, then instead of having separate carriers, we keep it as an exciton. The interaction is strong enough relative to the size that it stays excitonic.
So there's sufficient electron hole overlap at all times that coherence is maintained, even though it's not strong enough to give a color shift.
Quantum. Yeah, that's right. That's right. Yeah.
Well, still, you mentioned that the absorption is increased in your large Perovskites quantum dots. Can you explain the physics of it?
It's a little bit like the G aggregate. You've got, it's kind of the equivalent of having super radiance from an excitation that's able to delocalize over multiple transition dipoles.
So it's a giant oscillator strength.
It's a giant oscillator strength, in fact, yes.
Okay. It's not clear to me why, when you get ordered G aggregates, the coupling with the surroundings is diminished. You would rather expect that when you have a long quantum system, quantum wave function, you would have more interactions. So can you explain why it gets narrower?
So it's the interactions of the excitation with the underlying atomic lattice of the dye molecules themselves that gets diminished. You still, as you say, you still have interactions with the bath. And so that is going to limit the delocalization. So the bath causes the sites to have site disorder because of the bath.
Okay, but you're talking about the interaction with the skeleton is diminished because of the localization wave. Okay, that's clear.
Because luckily the excited state wave function is diluted, so there's a weaker electron lattice interaction locally.
Yeah.
Okay. So when you describe your measurements, you seem to address individual quantum dots.
Yes.
Okay. Whether for your perovskites, it's not so clear that you could specially resolve them. They looked quite near each other.
Okay, so yeah, the image I showed was not the sample that we studied. The image I showed is just so that we can see a lot of them together packed up. But when we do the experiment, we dilute them out so that they're many microns apart, so we can look at each one individually.
Okay. So if you have a giant oscillator strength, then it should be very easy to get strong coupling in a microcavity.
Yes, so we're working on that. So we need a plasmonic microcavity because in order to get the Purcell effect, we need a very small volume in the cavity at this wavelength, because we're in the 500 nanometer range for the light to come out.
People have used photonic crystal cavities also.
Yeah, we're looking into that as well. We're looking for something as simple as possible right now, and making a 2D photonic crystal seems like more work than we should need to get the effect that we want.
Not on paper in MIT.
Yes, right, but you're absolutely right. That would be the most elegant way of doing it.
Okay, so So do you have any way to look at the effect of increasing the size of your quantum dots, and indeed going from the fully quantized electron and holes systems to delocalized electron and holes, and maybe you would have first the delocalization of a hole, then the electron. Is there a way to increase your quantum dot size?
So experimentally, if we wanted to, we could spend time to do that. We have not done that. So, but that's a really interesting question. The question is, is there an optimum size? And 10 nanometers is probably not the optimum size. Probably a little bit bigger is better. But we haven't done that.
Yes, the idea is you want to have the largest quantum dot to have the largest giant oscillator strength without losing the coherence because you are too big for the electron and hole wave function.
So you're probably going to be just at the limit where the sort of size confinement is just about to operate, but not strongly.
Yeah.
No.
Because you don't want to have, you don't want your carriers to fall apart. You don't want your exciton to fall apart to create.
Exactly right. So you want to keep the electron hole together. So you're just at the point where you get some color changes if you were to make the dot smaller. I think the literature suggests that 10 nanometers is about that number.
Yeah, but we're at low temperature. We're at 5 Kelvin, and so at 5 Kelvin we might be able to go bigger than that.
Okay. Yeah.
You went a little fast on your entangled photons.
Yes.
Can you remind us how you got entangled photons you had by Exciton? It wasn't clear for me.
So if you take a stream of photons, let's say from one of these particles, and they're indistinguishable, then you can time two sequential photons and separate arms of, let's say, of your experiment to come together spatially.
Yes.
So you emit a photon, you emit a second photon, and you're using a pulsed laser to excite them. So you know the timing difference between these photons. And so you can now take these two photons and by changing the delay arm on one versus the other, you can get them to spatially overlap in a beam splitter.
But why do you call them entangled?
Because if you have indistinguishable photons that spatially overlap, they become entangled if they're indistinguishable. You get constructive interference of the two photons, and they become entangled.
Okay.
They're truly, purely in phase and indistinguishable. And then they come out together instead of separately.
Okay.
I thought with the 3-5 dots, there had been a huge effort to be able to engineer biexcitons to be able to achieve that entanglement.
There's also a way there's a biexciton cascade, which also allows you to have entanglement, which is somewhat different from the spatial entanglement that I was talking about. That's correct. And we're looking at biexciton cascade as a way to get entangled photons out of these materials as well.
So what about biexcitons in your Perovskites quantum dots?
So you can create biexcitons, and you can adjust the formulation of the perovskite dots to either have a very high biexciton quantum yield, meaning that so one of the ways that you can destroy biexcitons is if one of the electron hole pairs recombines and gives this energy to the exciton. And that's an Auger-like process. And that can be very fast with the 2,6 materials, unless you can engineer the material to prevent this process to be too fast. And with the very red perovskite dots, that process is slow, and you can see very high biexciton. The lifetime of the biexciton is long. With the blue ones, the lifetime of the biexciton turns out to be quite short. It's still long enough that at low temperature, we have to filter out the biexciton photons from the exciton photons. Because you get a cascade. Your biexciton, you emit one photon first and then the second photon. And so you want to get rid of that first photon because it has the wrong energy and keep the second one.
Well, unless you want them to be degenerate.
Yes, yes. So you can have a Bawendi cascade, and you can put an electric field on the material to try for that to happen. That's a slightly more complicated experiment, which we're also thinking about.
It would work. Okay, an electric field would do the job.
An electric field would switch out these levels just ever so slightly to get them to be degenerate. Yeah.
Oh, that's interesting. Okay.
There are 2 questions in the chat.
Okay.
Sorry, before we do the questions, may I quickly suggest that we do have we do have individual discussions for different topics after this, which roughly starts around in 7 minutes. So Catherine posted all the links on the Zoom, on the Waves webpage. So if you scroll down to the schedule, you will see all the Zoom links for each individual topics and the title and the sort of a quick description of each individual topic. So if you're interested, just click on the Zoom link, you will go to that. So it's not like a breakout room, but with honest individual Zoom links. So that thing is supposed to start in about 5 minutes. So for those who are interested in keep on discussion, you can stay in this room. And for those who are interested in going to a different room with different topics, feel free to just leave this room and go to the other link. Okay, and sorry, Marcel.
No, I just said that they were in the chat.
A couple questions. So if I read the first questions, the first question about transport in quantum dots. So quantum dots have much higher static disorder than G aggregates, and we see hopping transport even at all temperatures pretty much. And then the amount of control. So we can control them from a few nanometers in size where the electron is highly confined to about 10 to 15 nanometers in size is the control we have.
I have a health question, Moungi,
Yes.
which Richard referred to very, very briefly in a sentence. What's the toxicity of the Perovskites and the other materials?
Yes, well, these are all lead-based Perovskites, and as such, they're regulated, and lead is not a great element. When we're talking about one quantum dot, we're not talking about very much lead. So the number of amount of lead that we work with on our slide is really extremely tiny, and I wouldn't worry about it.
But I mean, if for an application like a solar panel or something like that.
Yeah, that is a really good question that the field has to grapple with.
Right.
I believe that's separate from my work, but my experience with working with companies, large companies with quantum dots made out of cadmium and other elements is that it's a non-starter for them. So it's a question of perception. Go ahead, Richard.
Well, First Solar has sold, I don't know, square kilometers of cadmium telluride solar cell.
But they wouldn't be able to do that. They wouldn't be able to start today.
I think they would. I think but they do sort of guarantee a sort of cradle to grave service.
Yeah, but Ross has an exemption for them, which is renewed every 5 years, and the Ross exemption is determined to whether or not there is another material which is less toxic, which can have the same properties. And I think they're very worried that one of these days, the Ross exemption will not be renewed. That's how Ross gets rid of lead in consumer materials, etc. So I'm not as optimistic as you that it would actually be allowed today.
I wasn't necessarily being optimistic. I was just making a statement that these things have been sold.
No, it's true. They've been selling, but that was grandfathered in, and the exemption was created.
And they're supposed to take back all the cells and get rid of the cadmium.
I believe so. Yeah.
They're supposed to take the whole life cycle.
Right.
About the toxicity of cadmium, okay, it's relative. Okay, you should know that many years ago, I think 30 years ago, yeah, 30 years ago, people in the labs put yeast in a cadmium salt solution, and the yeast cells fabricated cadmium selenide quantum dots.
Yes, cadmium sulfide.
So
Yes, that's true.
to protect themselves, because as a quantum dot, the cadmium is not toxic. It is when it is free. But of course, it has a limit. If you put too much cadmium in a solution with yeast, of course, the yeast cells will die. But as a first protection, we will fabricate quantum dots, very nice quantum dots.
Yeah, it's true. That was a guy named Dance that did this in 1980.
Cameron in 80-something, yeah.
Yeah. So, I mean, this toxicity issue is a very complicated one because there's the science, there's the reality, and then there's the perception and the public relations. So for the TVs, Sony was the first company to make quantum dot TVs. They use cadmium. Samsung would not touch them, the cadmium. Samsung developed non-cadmium based quantum dots. Sony stopped making them because they were afraid of having a PR nightmare on their hands, especially in Japan, with the experience that Japan had with cadmium poisoning. The cadmium that was in those TVs was completely inert. You know, it was in glass and everything like this. Even if you just put it disposed of it in a municipal dump, it wouldn't go anywhere. It was just, you know, but the perception of it.
Yes, it would stay as quantum dots.
Yes.
Okay,
you know,
so the other quantum dots are, as I understand, a little less efficient. But for TVs, you don't care so much about the efficiency.
Yes, the lifetime doesn't, well, it's a question of lifetime. They don't last as long. They've gotten to be as efficient. They're not quite as robust.
Okay.
But it's a trade-off.
Okay. Okay.
For instance, you know, I was working with Samsung on a different project having to do with photodetectors, and you know, and I wanted to put lead in my material, and they said absolutely not. And I said, but you put arsenic, you know, as a chemist, arsenic, lead, it's all the same to me in terms of toxicity. They said arsenic is okay, lead I can't use.
Okay, but to make those non-cadmium quantum dots, was the experience in cadmium sulfide quantum dots useful?
Of course, yeah. The basic, the basic photophysics is the same for these 2.6 and 3.5s. It's roughly the same. The chemistry is different. It's harder to make the 3.5s compared to the 2.6s, and so that took a lot of work. And it took Samsung, you know, 20 years of work to get to where we are today.
What is the material?
Indium phosphide.
Okay. Well, indium phosphide was something.
With zinc selenide and zinc sulfide.
Okay.
But I think they're going to be in trouble because indium phosphide is on the Ross hit list for the next few go-arounds.
Is it? Which one? What, for the...
phosphorus, come on.
As a potential carcinogen.
Everything is carcinogen.
Yeah, well.
Gallium arsenide also.
Of course.
Maybe not silicon.
In small enough, you know, particles, if you inhale it.
Well, silica, small particles, is very toxic. Yeah.
Okay. Very good. Well, Moungi, thanks a lot for a great talk and great discussion.
Well, thank you.
Yes, thank you very much.
Yeah, absolutely.
Thank you. Excellent.
Thank you, David, for inviting me.
Yeah, very, 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 my pleasure. Great.
Okay. So
Okay.
thanks everyone for the first afternoon discussion, and thank you again, Professor Bawendi, for coming. And as I said, there were different links for the Zoom chat for different topics. You can see them just on the website. I think Catherine also put them in the chat room as well. You can just click on the link. All right, so I hope everyone can find a topic that's interesting to them and enjoy the rest of the day for the discussion. Thank you all.
Thank you. Thank you, Megan, for helping me out also. Bye, everybody.
Thanks.
Bye.
Bye-bye.
Bye.